I'm going to talk about whether quantum computers, or raise questions about whether quantum computers can help with general artificial intelligence. This is a, it encodes it as a set of quantum bits, and then it has this superposition of waves corresponding to the quantum parallelism within the computation. And then at the end, it comes up with an answer and it says, hey, it's a cat or it's a dog. This is actually, of course, just a simple kind of machine learning problem. And I'm going to spend most of the time arguing that quantum computers could be quite useful for machine learning, or raising the question of whether they might be useful and giving the arguments for why they might. As we heard from the session on quantum computing, full purpose, full scalable general purpose quantum computers are between 15 plus or minus never years away. But we have devices right now that might actually be quite useful for looking at patterns and for finding patterns in data we couldn't find classically. And I also feel that general strong artificial intelligence is at least 15 plus or minus never years away. I'm actually going to argue that I think it's probably considerably more than that. And this makes quantum computers a natural companion for strong AI, and that they're both a long way in the future. It's like, gallium arsenide was the material of the future for decades, and then graphene came along to keep it company as the material of the future. So quantum computers and strong AI are both intellectual materials of the future. And for that, I think it's okay then, since I believe, and I will argue for this, and I'm sure we'll have dissenting opinions about this, that we have a long time to think and worry about how quantum computation might fit in with strong AI, and so we can go and take a look and just imagine what might happen. Some of it is good, some of it is bad. All right, so let me talk about quantum machine learning. I've been working on this topic now for almost a decade. I became interested basically my postdoc Patrick Rebentros came to my office one day in around 2010, 2011 and said, hey Seth, we should work on quantum machine learning. I said, great, what's machine learning? Because I didn't really know much about I knew what it was basically. That is that it's using computers and other computational devices to try to find patterns in data. But I didn't know how it was done. And when Patrick started describing to me the various ways that it was done, I said, oh yeah, we can quantize this. And the basic picture, I'm going to argue that why one might think that quantum computers might be useful for doing machine learning and maybe doing things better than classical computers. Quantum computer systems can generate patterns that can't be generated classically. I mean, this has been known for a very long time in the context of questions about locality and entanglement. And more recently, thanks to Scott and other people in the context of what's called quantum advantage or quantum supremacy, shocking and horrifying name, I hate it. But the idea is that, and the idea is a very lovely and simple one, it's that if I take a quantum system, like this is a picture of a set of ions in an ion trap with their nuclear or electron spins or hyperfine levels, they have waves, they interact via vibrations, and you zap them with light, thereby programming them to perform some kinds of controlled set of interactions, which can be a quantum computation, and then you measure the outputs. The statistics of the outputs under plausible assumptions of computational complexity could not be generated by any classical device. That is, quantum advantage says that the statistics that come out of quantum systems are inaccessible to classical devices equipped with random number generators. And this is a remarkable feature. And so, but quantum systems can generate patterns that can't be generated classically. So maybe they could also recognize patterns that can't be recognized classically. And here you see the reverse process. We have some bit of data coming in. We load the data onto our ion-trapped quantum computer, and I'll describe in some detail about how you can load data, classical data, onto a quantum computer. And then this performs some set of computations, or some kind of quantum logic operations, and then it says, hey, it's a cat. This is, you know, of course, the most famous problem recently is when the Google DeepMind people managed to train or have a neural network look at data from the internet and spontaneously realize that there were lots of pictures of kittens out there. And then it was very good at recognizing these pictures of kittens, though, may I say, from a Bayesian standpoint, because the prior probability of a picture on the internet being a kitten is so high that, you know, I'm not quite as impressed as I might be. So that's the simple reason why this is the case. Because if you look at, for instance, deep neural networks of the kind that were being used to recognize, figure out that there are lots of pictures of kittens on the internet, they can generate patterns, and then they can recognize patterns, and there's a strong overlap between the set of patterns that they can generate and then they can recognize. So for instance, if I train a deep neural network to recognize pictures of kittens on the internet, and then I show them a picture of Max and say, what do you see? They would reproduce a very kind of kittenish picture of Max, which Max is kind of a kittenish kind of guy already, I'd say. Cute and playful, and but with sharp claws. So, all right. Let me give a second reason why we could why we can reasonably expect quantum computers to do better than classical computers for recognizing data. And this, of course, is these are the methods that Patrick and our other collaborators and I have developed over the last decade or so. And this is, as well known, quantum computers are good at linear algebra. In fact, not only are they good, they're really good. And here there's a very, why are they good at linear algebra? It's because quantum systems and quantum mechanics is all about linear algebra. The states of quantum systems are vectors in high-dimensional Hilbert spaces over complex numbers. And when they evolve in time, you multiply these vectors by matrices. And quantum computation comes because if you can control the matrices by which you're multiplying these vectors, then you can perform all kinds of linear algebraic kinds of things. And let me just go down this list right here. Classically, let's look at linear algebra. We have vectors in some high-dimensional space over the complex numbers. If it's c to the n, we need order n bits to encode these vectors. And then we can do things like fast Fourier transforms, which are very fast. They take order n log n operations. But if we have the corresponding quantum vector in this high-dimensional Hilbert space, because this quantum vector only has log n quantum bits, so the point is that the dimension of the Hilbert space goes as 2 to the power of the number of qubits, then I can have a small number of quantum bits, and they can inhabit a huge, as our president would say, vector space. So for example, 1 qubit is a 2-dimensional space, 2 is 4, 3 is 8, 10 is 1024, 300 qubits inhabit a 2 to the 300 dimensional vector space, and 2 to the 300 is around 10 to the 90, which is the number of microwave photons in the visible universe. It's the number of elementary particles in the universe, so these are large vector spaces. Anyway, the fast Fourier transform takes order n log n ops, but the quantum Fourier transform performed on log n qubits takes order log n squared. It's exponentially faster. And similarly, finding eigenvectors and eigenvalues of sparse matrices takes something like order n squared ops. On a quantum computer, it takes time order log n using the quantum phase algorithm. Now, we can also invert matrices. This takes time order n log n ops for sparse matrices, if A is sparse. On a quantum computer, again, doing the quantum version of this takes time order log n. And this means that there are all plenty, since many data fitting and machine learning protocols involve simply manipulating vectors in high-dimensional vector spaces using linear algebra. It means that we can do things like support vector machines, which is drawing the optimal separating hyperplane between two clusters of data, or data fitting, doing, say, a least squares fit of data in a high-dimensional space, Or principal component analysis, finding the singular vectors and singular values of covariance matrices for data. Or for that matter, finding topological features of data. These are all exponentially faster on quantum computers than on classical computers. As long as you can map your classical vectors of data into quantum vectors of data. And let me just say briefly about how this can work. This, of course, and I think Scott mentioned this, this is the key bottleneck in actually making quantum machine learning work. If you want to apply quantum computation to big vectors of classical data, you've got to get big vectors which are represented physically in some large thing into your teeny-weeny quantum system. So, and let me actually just give some figures of merit for this. Remember what you're doing is you have, say, an array of ions on an ion trap or superconducting qubits in a chip, like the kinds that are being built by Google and IBM and Rigetti. Or you have an array, a linear optical array with tunable parameters in the array. And let's say we're going to zap it with light. So we zap it with laser beams here, with microwave signals here, again with laser beams that could be creating things like squeeze states here. And let's simply ask, so what happens is we have some vector, we apply some set of pulses that are band limited. There are a certain number of channels, a number of ions that we can get there, and we can actually apply them for the coherence time of the system. And we get out some quantum state, psi, which is a function of this x, and whatever method we choose to zap these qubits with. And so if we ask how many bits we can get in, the total number of bits we can get in is the bandwidth of the system, which is the rate at which we can modulate the light to address the qubits, the number of channels, so for instance the number of ions we can address, times the coherence time of the system, so how long we have to actually get the information in. And here are some figure of merits for a bunch of well-known systems. So let's suppose that all our systems have, say, 100 qubits, which is basically what we have right now for these superconducting systems and for ion traps and for modes of optical systems. And the bandwidth differs from system to system. For the actual effective bandwidth is around 10 megahertz to 100 megahertz for ions. Coherence times is seconds, many seconds. So you can get in around 10 to the 9th, or actually if you go up to 100 megahertz, 10 to the 11th bits into an ion trap, into its coherence time. You can get around, they're about, it's 10 gigahertz is the bandwidth of superconducting systems. The coherence time is currently on the order of 100 microseconds. You can get around 10 to the 8th bits into a superconducting system to encode it as a quantum state. Similarly for these quantum optical systems, if you have 100 modes, 10 to the 14th per second. You can put them into the optical chips over times that are around, 100 nanoseconds or something like that. And again, you get 10 to the 8th. Or they're all about 10 to the 8th, or in the next few years, they could be as much as 10 to the 10th. Now, this is way more than enough to load a picture of a kitten onto a quantum computer. That's, I think, the point that I'd like to make. So I think right in the near future, we will have the ability to load classical information onto various quantum systems that exist now or will exist in the next couple of years, and then do quantum machine learning protocols on them. And as an example, let me just say, here's an example of an algorithm that I've recently been developing with the folks at Xanadu, a quantum startup in Toronto, which deserves to be invested in because it doesn't have a Q in its name. The only ones that don't have Q in their name are Xanadu and Zapata. So I think you should definitely look at those. So the idea is what I call adaptive quantum embedding. So if we go here, you see what happens is we have our vectors. We choose an embedding by a classical strategy of zapping our ions or our superconducting circuits with some light. And so we have a bunch of parameters that we can do to choose this signal we go in. And I'm going to call these parameters a W, a set of weights. So we map our vectors onto quantum states. And then we're going to vary the way in which we embed this. This variation is all done completely classically. It's just choosing the set of classical pulses we put in. And our goal is to map all the cats into a cluster over here in Hilbert space and all the dogs over here. And then it's very simple. One of the simplest protocols you can do on a quantum computer is to make the optimal measurement to distinguish between these states. This has been known since the 1970s, and there's a very simple quantum protocol, quantum algorithm for doing this. And then you just measure. You say, are you in this cluster or are you in that cluster? We decided that the cats are X's because they have whiskers, and the dogs are O's because they have noses. Okay, so that's what they're right here. So this is a simple quantization of a support vector machine. Any bipartite measurement identifies a separating hyperplane in Hilbert space. And we know the optimal measurement once we've embedded these things. And so we just embed them, and we then see if we can distinguish them. And then we vary the embedding to try to make this better. And then results of quantum advantage or supremacy simply mean that these embeddings, these mappings into these vectors in Hilbert space, these are not accessible to classical computers. So these are embeddings that classical computers couldn't do. Now, will this work better than classical computers? I don't know, but it's provably different. That's the important part here. So, because quantum computers have access to embeddings that are inaccessible to classical computers, maybe they do better in these kinds of machine learning tasks. And we're going to find this out soon, because this is stuff we can do over the next few years. All right, so this is my last slide here, because I want to talk about strong AI and versus strong quantum AI, which I've expressed in both chess and Spanish chess notation as being questionable and amazing. And here is my picture of my classical computer driving a self-driving car versus my quantum computer driving its self-driving quantum car in a quantum superposition of left and right at the same time, as in the famous bad physics joke, Professor Heisenberg, did you know how fast we were going? That's what the traffic cop says to Heisenberg, having pulled him over, and he says, no, but I know exactly where I am, right? or the other version is, Professor Heisenberg, did you know you were going at 200 kilometers an hour? And Heisenberg says, God damn it, now I'm completely lost, right? So, do quantum computers give us something for strong AI that classical computers don't? Well, potentially yes, because as I've just argued, they can actually find patterns in data, or ought to be able to analyze data. They can analyze data in ways that are not accessible classically, that is not accessible to our own brains, for instance, because our own brains, Pache, Roger Penrose, and Stuart Hameroff, our own brains are extremely classical systems and process information in a very, very classical way. But in the long run, if we enlist quantum computers into doing problems involving artificial intelligence, then maybe they can do things that are different. Now, let me just say, since Max has said I only have 2 minutes, let me just say a word for why I don't believe strong AI is going to be here anytime soon. First of all, empirically, empirically meaning looking at the historical record, AI has habitually overpromised tremendously. You know, folks like Marvin Minsky, who sadly passed away this last year, were promising back in the 50s we would, not only we would have computers that could play chess, we would have, which people were making progress on already in the 1950s, but we would have robotic maids which would be cleaning up your room. And by the mid-1990s, we indeed had a computer, Deep Blue, that beat Garry Kasparov, the world champion in chess. But the closest thing we had a robotic maid was a little Roomba that moved around at random and would go squeak, squeak, squeak when it got caught under the couch, right? And we still don't have anything remotely close to something, a robot that can go and clean up your room. Partly because, I don't know about you, but I personally have had in the course of my life, for about 10 years, I had teenage daughters. And from looking at them trying to clean up their room or failing, I would call this at least an NP-complete problem and probably uncomputable. But this is why I think that, so my prediction for AI is, in some sense, we're already using machine learning and artificial intelligence in our daily lives, because again, if you have a teenage daughter and you see them, and by the way, teenage sons are like this. I just happen to have daughters as well. I'm not picking on any gender here. They're glued to their smartphones, and they're spending their entire time interacting with their best friend, which is their smartphone. And the smartphone talks to them and reinforces them and gives them, positive reinforcement, and so they interact with them even more and takes up even more of their time. And so these are very rudimentary artificial intelligences. They're just using, the power of Google and other places to spy on us and do machine learning to, try to figure out ways of getting our attention. But they're very good at that. So, I would see something more that are actual physical information processing artifacts. As they learn to process information more efficiently, they will become more and more part of our society. And our tendency will be to treat them as if they are intelligent, whether they have consciousness or not. But this is going to take a long time for them to actually reach anything remotely like artificial intelligence, where these machines actually have consciousness, perception, free will, depending on your opinion about free will, etc. And this also will be true for quantum computers. However, when we do get if we ever do get strong AI, which might very well be, after we have scalable quantum computers, then quantum computers might be able to do things and be, artificially intelligent in a way that is inaccessible classically. Thank you.